Okay, thank you. Okay, so let me explain the plan of what I'm going to try to say. So actually, originally I had a slightly different plan, but then I somehow realized that in this school, nobody is actually talking about the subject of symplectic duality, so I decided to basically devote the first lecture to mostly discussion of this subject. So the plan for 2 lectures will be following plan. So part 1 will be sort of, let me call it naive. Press on what? Introduction to symplectic duality. And so let me just say one word right away here, just in order to explain the other parts of the plan. So this will be sort of about pairs of dual, in some sense, which I'm going to at least partly explain, pairs of dual objects, let's say X and X check, which naively are going to be some kind of single symplectic varieties. Again, I'm going to say more precisely in a few moments. But again, I want to stress this is a very naive thing, because the correct thing is some kind of much richer structure, which I'm going to try to say something about later. So this will be part 1. So just introduction of what symplectic duality is, what people mean, at least partly, when they talk about symplectic duality. Then I'll probably then spend quite a lot of time talking about examples. Then I'm going to briefly again explain some construction of these guys in a certain, in a certain class of examples. Construction. This is my joint work with Finkelberg and Nakajima. Construction of the symplectic duality of symplectically dual pairs. Construction. Dual pairs. And then we're going to kind of switch gears, and so then there will be parts 4 and 5. So it will be part 4 and maybe 5. So part 4 will be sort of, so by switching gears, I mean that then we'll try to sort of look at this differently and try to think about what kind of structure is really responsible for the appearance of this stuff. And so a physicist would say here that the correct structure is this something which is announced in the title, and this is this 3-dimensional, some kind of supersymmetric quantum field theory. So part 4 will be some kind of linguistic introduction of I would say I should try to say some mathematical structures related to 3D n equal 4 supersymmetric quantum field theory. So here, linguistic means that somehow, so there will be no mathematical quantum there, but there will be just words. So somehow, in other words, so what I'm going to it will be of the following. I mean, that will probably be next time. So somehow the style of this will be the following. That somehow I'm going to basically tell you. So this. In part 4, this quantum field theory will be treated as a black box in the following sense. I'm going to tell you that you're supposed to be able to construct it out of some data, then there will be some operations on this quantum field theories which sort of take all the quantum field theories and produce new ones. And then I'm going to tell you somehow that what kind of mathematical structures they're supposed to produce as an output. So there will be some kind of input, some kind of output, and in the middle will be a black box about which in part 4 nothing will be said. And then part 5, which I don't know if I managed to get there or not, this is some kind of recent work in progress with Kevin Costello. This is an attempt, so try to, well, at least give some hints, try to treat part 4 mathematically rigorously. And the point of part 4 and then 5 is that it's actually going to eventually, well, at least it's supposed to eventually contain everything we're going to talk about here. Okay, so this is kind of the plan. So now let's start with part 1, and let's forget about everything, and let's talk about part 1. And actually, before we talk about duality, let me recall a few things about single symplectic varieties. In fact, so I'm going to, in fact, talk about conical things, although in some examples somehow things will not be conical, but somehow it will be easier for me to explain what we want in the conical case. So somehow, first of all, let's suppose that X is an affine, let's say, normal Poisson generically symplectic variety. So there's a standard definition which says that X is, I don't know if this has already appeared in some of these lectures, that X is, this definition due to Baville, that X is called singly symplectic if there exists a resolution or equivalently for any resolution, if for some resolution or equivalently for any, let's say there exists X tilde to X some resolution. So generally symplectic, so here that means that there's a symplectic form omega, resolution such that pi star of omega has no poles. Of course, interesting thing for us is when we have a symplectic resolution, although that at least somehow I would like to treat the case when there is a symplectic resolution as a kind of rare luck, has no poles. In this case, somehow it's known that X is a union of finitely many symplectic leaves. And well, I'll pass to examples in a moment, but before that I want to give talk about some general.
Here you don't use that it's conical.
No, I'm going to do no. Here you don't need that it's conical, but so I'm going to assume that the thing is conical in a moment. But again, in some interesting examples, somehow some of these things will not be conical. But let me just, for simplicity, assume that's conical. So I assume that there is a C star action on X which contracts X to some point 0 in X, and which dilates the symplectic form. So somehow says omega has positive weight. So in this case, one can attach two vector space, canonically two vector spaces to X. So when we're going to attach two vector spaces, I'm going to, well, let's say real vector space. You can either real. In fact, they're going to also have canonical integral lattice inside them. In fact, they'll have more structures, for example, in hyperplane arrangements. So these are two vector spaces. So one vector space is easier to define, although somehow it's usually difficult to compute it rigorously, although it's often easy to guess what it should be. So namely, you take this Tx is going to be the following. Well, let's even talk about complex vector spaces. So let's consider let's G be the group of Hamiltonian automorphisms of X, and let's T be its maximal torus. Yes, commuting of, well, of X, okay, let's say commuting of the whole structure. T is a maximal torus, and so T sub X is going to be its Lie algebra. Now, to define Sx, I'm going to, let's assume that X has a symplectic resolution, although we can actually define it, there's a rigorous definition due to Namikawa without that assumption, but it's easier to say what happens when it has a symplectic resolution. So, so if pi from x tilde to x is a symplectic resolution, then Sx is going to be the second cohomology of x tilde. Let's say, okay, let's talk about complex vector spaces. So let's do with complex coefficients. But in fact, it's clear from here that they both have actually integral structure. Now, a standard fact in...
Is it independent?
Yes, this was my next sentence. So the standard fact in this theory is that this is canonically independent of the choice of x tilde. So it does not depend on x tilde. And in fact, it can be defined without the assumption that there exists an x tilde, but basically you can, instead of x tilde, we can, such an x doesn't necessarily have a symplectic resolution, but it has something, some kind of symplectic thing, which is, it should take x tilde, which is as non-single as possible, so to say, and there's a kind of rigorous sense to that, but let me not go there. Something like that, but yeah, but okay, let me not go into that. But okay, maybe.
Do you need assumptions if it's single symplectic in your sense?
That's kind of the only. That's the only sense which exists. I don't think there's any other sense.
And final last question. So you said union find the many symplectic please. What does symplectic please? You have singularity. You have two form on X. So what
No. I mean, okay. If you have a Poisson variety, there's a notion of symplectic leaves and a leaf in any Poisson.
you say it's Poisson.
As I did say.
Oh, okay.
Okay, so maybe it makes sense to give one example already at this point. So one example is the following. So suppose that G is a simple Lie algebra, let's say everything over complex. Yeah, I forgot to say we're of course doing everything over complex numbers. So simple Lie algebra, and so we can take X to be the nilpotent cone. So, well, in this case, you can show that this sort of, so to say, G is equal to G. Namely, so this group of Hamiltonian automorphisms is really sort of, well, okay, G is the corresponding adjoint group, and T is equal to Hamiltonian automorphisms of X. And so in this case, T sub X is equal to T. This is the Cartan subalgebra of G. Cartan subalgebra of G. And of course, this has a natural symplectic resolution, namely the Springer resolution, and which shows that immediately that S sub X in this case is T dual. So I should point out that in this case, somehow you see that these two spaces are dual to each other, and particularly have the same dimension. That's actually a coincidence. That's not going to. I mean, usually there will be absolutely no relationship between these two spaces. Okay, so more examples will come in a few moments. But let me just say, yeah. So again, let me remark the following, which will only sort of become important tomorrow. But in the true theory, of course, I mean, X is just treating X as a symplectic variety is a little bit too naive. So in fact, somehow there should be more structure. Sometimes you should remember more structure. So sometimes it should be some kind of symplectic stack or even symplectic DG stack, and this will really become important next time. But so far, let's do this naive thing. So we should. And so what is this first approximation to the idea of duality? So often. Oh, sorry, I forgot. Yes. So often, one can find some x tilde, x check, which is some kind of similar object, again conical, let's say symplectic variety, which as a first thing, first approximation, I would like to say that it has the property that s sub x, s is the same as t x check, and t sub x as s x check. But of course, we want much more than that. So let me say plus much more, and I want to say a few things about what this much more is. Now, perhaps it makes sense to mention this example, but again, I'm going to construct a lot of other examples in a moment. So maybe before that, let me just say about this much more. So this much more will, there will be kind of two different types of additional things that I would like to have. And so there will be kind of geometric things and categorical things. So categorical things will be related to studying categories of modules or quantizations of these varieties, and geometric things will be really about the geometry. And in principle, in true theory, somehow all the geometric things should be applied by the categorical things, although this is not really understood yet. So I'm going to explain some of the geometric things and some of the categorical things. I mean, what do you want from the situation? But somehow there's no good understanding how to somehow get all the geometric facts from the kind of categorical facts.
One more question. So your G, if you assume it's a reductive group, I understand what maximal torus is.
Maximal torus exists in any group.
So if you take, for example, C to N, so the standard symplectic structure. So there is a symplectic group and translations. What will be your torus?
No, it's supposed to commute with the C star action. So somehow.
But we assume that G is reductive.
No. In this case, this is fine dimensional. This is not fine. This group is always fine dimensional. So any fine dimensional group. No, I mean, in that case, yeah, but in general, I mean, I'm not sure it's always. I mean, I don't think it's always. I mean, I don't see any reason why it would always be reductive. But it's a fine dimensional algebraic group. It has a canonical maximal torus. I mean, it has canonical Cartan group.
But in any case, only reductive part matters.
That's also true. But the point is that if just you can prove that this group, the way I define it, is always fine dimensional. That's kind of important. Okay, so. Now, what did I want to say? Yes. I want to produce a little bit more examples before we continue. Okay. So let me just see what kind of examples I want. Yes. Yeah. Well, I mean, formally, I want really to be Hamiltonian. I mean, that kind of with canonical moment map. There is such a notion. There's a notion of Hamiltonian. Okay. Well, okay. Let's say. I mean, in this case, it's probably the same as just preserving the symplectic form. So one sort of source of constructing such axes could be the following. So suppose they have G some, let's say, reductive group, and historical reason to denote this guy by M. M is a symplectic representation of G. For example, M can be equitangent bundle to something where N is any representation. Then we can take X to be the Hamiltonian reduction in the kind of categorical sense. So this is just the spec of invariant functions on the preimage under zero of the moment map. I'm sorry? Nakajima claims it does, although I've never seen a reference, but so I don't know. I mean, I'm not sure. I mean, very often it definitely does, so I don't know. I mean, I can't give you a reference that it always does, but somehow Nakajima claims that he knows that it always does. So in particular, all Nakajima quiver varieties arise in this way. So all quiver varieties in this. I should mention that this BFN construction that I mentioned, it really constructs the symplectic dual, well, in this generality in some kind of uniform way. But for quiver varieties, sometimes you can say things more explicitly. So first of all, what is the situation with quiver varieties? The situation with quiver varieties is that what is G and what is this thing? So assume that we have a quiver Q. So we have some vertices and some arrows. So let me actually, for simplicity, choose an orientation of the quiver. Let's assume that's an oriented quiver. And so we're going to put some vector spaces at the vertices of the quiver. And also we're going to put a framing. So that's so we're just going to choose another vector space for any, I mean, everything's fine dimensional, attached to sort of leaving over every vertex. And maybe we should look at arrows like this. And then, as usual in the Nakajima construction, we should double it, but the doubling will sort of correspond eventually to taking this cotangent bundle. So formally what we should do is that we should take this, first of all, G is going to be product over all vertices of the groups GL VI. And M is going to be direct sum over all edges home from VI to VJ plus direct sum over all vertices home VI WI. That's a quiver situation, and so in this case, it kind of depends on two actually vectors. So if I is the set of vertices, then we can consider dimension vectors V and W, which are both belong to Z greater or equal to 0 to the power I. So this quiver variety depends on this data, and somehow, I mean, this is like in Vani's lectures, and there's in many other lectures here, so we can ask so I'm not going to say what S and T are in this case, but I'm going to or tell you an example what will be a symplectic dual in this case for quivers of finite type. And that will be also my opportunity to introduce the affine Grassmannian, or also introduce some other conical symplectic varieties. So, maybe before that, I want to say that I want to give you examples of the pairs of symplectic duals before I explain what symplectic duality really is. So, one example is, so I said that one example of a conical symplectic variety is nilpotent cone of some Lie algebra, and here the dual is supposed to be nilpotent cone of the Langlands dual Lie algebra. And here I have this S and T space, T and T star, and here they're interchanged. So now I want to construct, I want to look at the case when this is a quiver variety. So let me make some assumptions here. So first of all, I want to assume that Q is a finite Dynkin quiver. And so I consider GQ, this is the corresponding group of ADE type. And then out of this V and W, we can construct two weights of this group. I can consider weight which I'll call lambda, which is going to be summation wi omega I, and mu, which is lambda minus summation vi alpha I, where it is a fundamental weights, these are simple roots. And I'm going to make an additional assumption that that mu is dominant. Assume mu dominant. So here, by the way, I mean, this is simply Lay's thing, so here I can identify weights and co-weights, at least if I work with Lie algebra. I want to explain what the dual is here. So here I can see the affine Grassmannian of the group GQ, which is GQ of K over GQ of O, where K is C of T. Always Taylor series. And then, well, as usual, this thing is a union of fine dimensional varieties over lambda, which are dominant co-weights of GQ, of things like this, where these are orbits of GQ. Oh. And we can consider closure of such a thing, and so this one of these guys lies in the closure of some other guy, if and only if mu is less or equal than lambda. And there is a kind of more or less canonical transversal slice here. So in this situation, there's something which is called double lambda mu. This is transversal slice to a small orbit inside the closure of a bigger one. And this thing is known to be single symplectic, conical. And that's the guy I should put here. And so that's another kind of source of examples. But I said that in this construction that I promised, somehow the construction is kind of very, very general. So in particular, it's also going to work even without the assumption that mu is dominant. So, and you can also compute what we get. Also it works even if you don't assume that Q is a finite Dynkin quiver. So we can actually define its transversal slices now for any quiver. Yes. Let me ignore this question. No, I mean this is okay. This is construction. This particular construction. This kind of. In this canonical sense, it's not that abstractly there's a canonical transversal slice. This is the transversal slice in this case. But I just don't want to explain what the construction is. And well, there are many other things you can do. So, for instance, you can consider here C2 mod gamma, where gamma is some finite subgroup of SL2. And to make the story more interesting, you can consider symmetric power of this surface. This is also some kind of conical singular symplectic. And so what kind of things should you put here? Well, okay, let me not explain too much about it. Let me just write it here. This is the Uhlenbeck space of, so G gamma is the group which corresponds to gamma under the under this Mackay correspondence, and this is the Uhlenbeck space of bundles on C2 with second Chern class n. So this is that's kind of just to give you the flavor of things which appear here.
I guess for gamma cyclic, we already saw it today under the name M of Rn.
Well, it's not exactly. It's the affinization of M of Rn. So I'm doing the singular things. Yes. This is this kind of the affine version of M of Rn. Yes.
So this is supposed to be a special case of the previous?
No, because somehow. Well, I mean, here I was only talking about finite type thing, quivers of finite type. This is also. I mean, it's true that this is a quiver variety, of course, and this is a. Okay, so this is a kind of example. So now let me talk a little bit more about what kind of structures we want. Let me actually talk first about categorical structures, because they're especially given some other lectures today. They're kind of easier to explain, and then maybe I'll talk about geometric structures.
What happens in the first example when mu is not
There's an answer. There's an explicit answer, but it will take me too long to explain.
So you also can construct something on that.
Yes, but it's not going to be conical in general. There's a definition. I mean, let's say this you will then go beyond, sort of out of the conical world. Okay, so categorical symplectic duality. Yes. By the way, there's also there's one other big class of examples, which are kind of always the easiest examples, which I forgot to say. These are called hypertoric varieties, and these are situations which are things of the form symplectic reduction of some symplectic vector space with respect to T, which is a torus. And here, I mean, this thing is given by some combinatorial data, and here it's easy to. Let me not go into this now, but it's sort of easy to. The dual is easy to define in this case. Well, yes. And that's actually sort of the best understood example. That's the only example where everything somehow. Everything I'm going to talk about is known completely. So categorical symplectic duality says the following. So when we have this X, we'd like to as again as one is lecture, would like to quantize it, and it's known that it has actually a family of canonical quantizations, and so this X, well, let's say that X is spec of some AX, and AX has a family, canonical essentially, family of quantizations parameterized by our SX. And I should say that SX also is responsible, so it's responsible for a family of quantizations. Also, there's also maybe, I'm sorry?
Family of quantization, formal quantization.
No, they're actually, I mean, because of the conical condition, they're actually actual quantizations. This is filtered quantization, as Wayne explained. So SX also parameterizes a canonical family of deformation of X itself. And also, I should say that partial resolutions, partial symplectic in the sense of singular symplectic, so partial symplectic resolutions of X correspond to integral points of Sx. So there's always some kind of relation between resolutions and deformations, and so here somehow these things. So anytime you have a resolution or a partial resolution, you can construct some kind of integral point of this Sx.
So is this known? I mean, I understand this probably well documented if there is a resolution.
No, I mean, no, I don't think it's known. This is not. Yeah, I mean, this is expected. I think this is formally known when all of this is known. If there is a symplectic resolution, if there is no resolution, I actually don't know. I mean, some of it is. Actually, some of it is known. I think that. I'm sorry. Okay, maybe. Yeah, no, this is definitely, if it's known, in the case when there's no resolution, everything is due to the Mikava, but somehow I don't actually remember what exactly, if all of this is known or not, but most probably, Okay, most probably yes, actually. But in any case, I mean, this is what I mean. I'm trying to explain what is expected in any case, because I mean, then we're going to pass to some constructions. Right. So then let's choose some psi an element in Sx. So that defines some kind of quantization a psi x ax. Well, like ax psi. This is a quantization. Now, I would like to talk about category O of this quantization. Let me actually, so here I will actually have to assume that there is a resolution. So I assume that there exists a resolution, x tilde. So this is symplectic resolution.
Your sentence interrupted. I mean, this sentence before, I mean, about partial symplectic resolution is kind of confusing. So you say they correspond to integral points, but
or rather to integral points. Well, maybe I should better way to say that to integral points we can no, right, I mean, okay, it's not all, yes, it's true that integral points some cone, but
they rather correspond to cones, right? Different points define the same resolution.
depends what you mean by the same. I mean,
So what do you mean by resolution, right? So resolution is a variety with a Keller class or something?
I mean, you're right. I mean, it's how to say this. So, okay, what I want to say is the following. So, I mean, the reason I'm going. Okay, let me just the reason I'm bringing this up is that I want to say that if you have an element here, so if you have the size integral, for example. No, actually, sorry. I mean, some resolutions correspond to different cones. But what I want to say is that if psi is integral, then it defines a partial resolution of x check. That's what I want to say.
For many different integral points in the same cone, the resolution.
That's yes, but again, I mean, the statement is true as stated. So and then
corresponds not even one-to-one, but it doesn't matter.
yeah, I mean, but again, this is true. I'm sorry.
I mean, the statement that you've written is more or less good. Why x check instead of that?
I'm sorry.
You have x check there, but you have x here.
Yeah, because the point is that this Sx. Sorry. Sorry. I got confused. Sorry. This is psi. No. Let me also. Sorry. Let's say eta in Tx integral. Then defines a partial resolution. No, here it's Sx. I mean, here defines partial resolution of x check because Tx is Sx check. Now, what I'd like to say is that so basically, now suppose that we have chosen both psi in Sx and eta in Tx, let's say integral, and then in a moment I'll have to assume that they. Yeah. By the way, maybe let me say one thing here, that what is in general expected, and is that so eta, if it's integral, so eta means that it's a co-character, so it defines a C star action, Hamiltonian C star action on x. So this is eta, and here there's some kind of partial resolution x check tilde eta over x check, and this guy is smooth. It's supposed to be smooth if and only if C star, only if this, let me say, eta has unique fixed point on x. So, which is equivalent to saying that if we choose a resolution of x, then they're going to have isolated fixed points. So the fact that you have isolated fixed points, this is what smoothness on this side is supposed to be seen by, in terms of fixed points being isolated. So now, if you choose both of these guys, integral, then, well, under the assumption that they're sufficiently nice, you can define some kind of category O here, this is a category of this is a category of modules over AX psi. So the point is that psi here appears as the parameter of the quantization, and eta appears in the following way. So if you think about category O for Lie algebras, then the notion of category O, sort of, in order to talk about category O, you have to choose a Borel. And this C star action is what defines a Borel. And you need, in order for this category to be kind of a nice category, you need this condition that there's a unique fixed point. Otherwise, it's not going to be a good category. So somehow, so I'm going to assume that psi is a nice parameter. So, for example, that it corresponds to an actual resolution of X. And I'm assuming that eta corresponds to resolution of X check. And then, under this assumption, you can talk about the category. So the conjecture is, well, for example, in all the cases that I stated, conjecture is that the category OX psi eta is Cazil dual to OX check. No, Cazil dual means Cazil dual. Well, I mean, it means that somehow that if you consider derived category, then there's a different grading, so that it means that that means that essentially means that derived categories are equivalent, but somehow with something funny happens to the.
Causal algebra, so that A modules are.
Well, that's kind of not, yes. I mean, one way is to say that.
It is causal in the first place.
I'm sorry?
In particular, each of those categories is causal in the first place.
Yes, in particular, each of those categories is causal in the first place. But in principle, it means that somehow, well, I mean, you can say it like this, that, I mean, one other way to say is that, for instance, if you consider simple modules here, then you can say the X algebra between them, that it's going to be equal to home algebra between some, say, projective or tilting objects here. Something like that. And so this is a conjecture that in this form is due to Braden, Proudfoot, Licata, and Webster, and it's known completely. Well, it's definitely known. I mean, sort of the example is this case when you have nilpotent cone of some Lie algebra, nilpotent cone of Langley's dual Lie algebra. Then, it's known in this case. This is kind of old work of Beilinson, Ginsburg, Zergel. And it's known in Toric case. Well, I mean, that's what I mean by toric. In fact, Nakajima strictly opposes the word hypertoric. So he's really ready to kill anybody who uses this word. He says that the right word is toric hypercalar. Toric case, so this is, I guess, Braden Proudfoot. And also there's a recent work of Webster which uses our construction of Filkenberg and Nakajima, which proves some slightly weaker version of this, but in a much greater generality. So it proves this version basically, for instance, for all varieties and for and basically in any case, in any situation when you have a symplectic reduction of a symplectic vector space, so it proves a weaker version, but under some very, very general conditions.
Sorry, in what generality is this category defined?
The category is defined, well, formally you can define the category just for any sign eta without any assumptions, but it's going to be nice, it has a chance of being nice category, like Cazil category and so on, if sort of the parameters are generic enough, and so the idea is that this psi corresponds to resolution of X, and eta corresponds to psi corresponds to partial resolution of X, and eta corresponds to partial resolution of X check, and you want them both of them to actually be resolution. Otherwise, something like this literally cannot be true. So somehow, I don't have time to do this now, but if you look at this work of Webster, somehow you can form some weaker versions of this, for which you don't need this, but for example, which are going to work when you don't have resolutions, but.
Don't have resolutions, it's like singular category O or something like this?
Well, yes, but somehow in that case you don't study category, but you just show that somehow some X algebra is equal to some home algebra, something like that. So,
These categories are always finitely many objects.
yeah, if you know under this niceness assumptions about sine eta, yes, I'm thinking.
Their highest weight.
I don't know. Are they always highest weight? And
You have finitely many fixed points. So
yeah, yes. In this case, yes, probably yeah. Yes. Okay, so that's the categorical thing, and now let me also talk about some kind of geometric facts relating. Some of them can actually deduce from these categorical things, but some of them I don't know how to do it. So geometric expectations.
When you given a category,
Yes.
when you find variety X, some kind of modulus space of something in the category.
I don't know. Well, I mean, you mean just any category of or highest weight category of.
But you want to. My question is, you start with kind of. Could you provide some categorical construction, which you start with your old set and you get your.
But what do you mean start with? I mean, you cannot.
No, but for,
I don't understand the question somehow.
if you take category of orthogonal group and symplectic group, they are equal.
Okay, so about geometry, you can there are many things you can say, but let me say a few words. So let me also assume that you have resolutions here. So suppose that you have a resolution, say x tilde of x. Then one thing you can do is you can consider this resolution. If it's a symplectic resolution, it's always semi-small, and you can consider the perverse sheaf, which is equal to the direct image of the constant sheaf. And this sheaf is going to be, it's a direct sum of irreducible, by decomposition theorem, direct sum of irreducible sheaves. And so irreducible sheaves which can appear here essentially have something to do with symplectic leaves of X, but somehow it's a little bit more subtle than that. So somehow any such sheaf is going to be actually supported in the closure of a unique symplectic leaf, and sometimes, but you know, these symplectic leaves sometimes are not simply connected. So some kind of local systems on the symplectic leaves sometimes appear. So in the case when this X is an nilpotent cone of some Lie algebra G, this sheaf is the Springer sheaf, which has of course been very extensively studied. And in the case, you can try to study this sheaf for any symplectic resolution, and at least there's some partial. So you can consider the set. You can consider the set of let's say Ix. This is the set of irreducible isomorphism classes of irreducible constituents of what we call it fx. So in fact, you can also show that fx is independent of the choice of the resolution. Sort of constituents of fx, and the idea is that, and there's some partial order here because each of these irreducible sheaves is supported on the closure of a unique symplectic leaf, and on the set of symplectic leaves there's a partial order which has to do with was given by closure relation. And so one thing you expect is that there's a bijection between Ix and Ix check, which is order reversing.
But this is a.
So moreover, I want to say something about it. I'm sorry?
It's a pre-order, yeah? I mean, because you can have several sheaves.
Yes. Yes. I mean, it's order reversing in the sense that if one is strictly bigger than the other, then after you apply the bijection, you will have the opposite thing. It's a partial pre-order. Moreover, you're going to have some kind of some nice properties of it. Well, actually, so suppose that we have now resolutions on both sides. So somehow we have resolution here and resolution here. Then one thing you expect is that dimension of the cohomology of X tilde should be the same as dimension of the cohomology of the dual guy. But there should be no canonical isomorphism between these cohomologies. So let me say something in the setting, so which sort of has to do with trying to construct a canonical isomorphism between these cohomologies, but will be sort of canonical isomorphism between some other things. Well, there's a check. Well, there's a check here, but maybe it's not.
X tilde goes to X.
Oh. So in particular, well, I mean, I have assumed that everything is conical. So suppose that you have some irreducible, some element here, some G, which is some irreducible constituent here, and then I'm going to construct some vector spaces attached to it. So one vector space we can construct, so to G I can associate a vector space which is the multiplicity, which is just, let me say, just home from G to this Fx. That's one vector space I can look at. Another vector space I can look at is the following. Well, okay, so I want to, so let me call this bijection somehow, let me call it alpha. So I can apply alpha to G. G is an irreducible constituent of this sheaf. This G is an irreducible sheaf which appears here. So I can apply alpha to G. This is an irreducible constituent of Fx check. Now here I'm going to say something which will use only actually resolution of X and not resolution of X of X check. So now a choice of this resolution is, as I said, is supposed to be the same as a choice of a C-star action on X check. So somehow choice of X tilde is the same as a choice of C-star action on X check. Given a C-star action, and moreover, it's a C-star action which has unique fixed point, with fixed point 0. And in this case, you can consider something which is called the hyperbolic stock of this sheaf at this point. So let me note. Well, maybe I can even define it. So you can then consider some subvariety Z in X check, which is just attracting variety to 0. Let's call this embedding I, and let's call the embedding of 0 J. And then we consider the hyperbolic stock is we can consider, say, I star J upper shriek of, well, I should say alpha of G. That's supposed to be canonically isomorphic to this multiplicity space. So a homework problem in Vanna's terminology is to check that this holds in the case of Springer resolution. So true in Springer case.
What is alpha in Springer?
Alpha is given by Springer correspondence. Well, it's alpha is given. Well, it's or more precisely, is given by Springer correspondence times the sign. I mean, just irreducible constituents. They correspond to a reducible representation of the Weil group, and the Weil group is the same when G check.
Different question. What is the pre-order?
No, it's always given by sort of. I mean, you can attach to this thing a nilpotent orbit. This is just given by orbit. So all of this is part of the homework problem. Yes. Yes.
There is kind of a finer thing. You can consider other category of other variant shifts on nilpotent column, which Springer is one piece, but in general there are some cuspidal pieces. do such things
I don't
exist?
know. I don't know. I mean, there's no abstraction to that. But what I wanted to say is that why, for example, I brought this up was that if you go back to this quivers of finite type situation, then if you consider this duality between this being x and x check being this transversal slice, then in this case, if you consider, you can consider the case when your G is just a skyscraper pointed at 0. So let me point it. So you can see the case when G is the just delta 0. And in this case, the multiplicity space, this home from delta 0 to fx, this is always the middle cohomology of the resolution. This is always h dim x x tilde. And this is this, well, on the other hand, if I can, this order, this alpha of g in this case is of course nothing else but just the IC sheaf of this guy. And the hyperbolic stock by the work of Mirkovich-Vilonen, stock by Mirkovich Vilonen is going to be the canonically the mu vector space in the representation with highest weight irreducible representation with highest weight lambda. And it's also this thing, and this is by the work of Nakajima. So, and these two things are, well, just on the nose the same. And for me, I mean, I should confess that for me, this was, I mean, this thing was the main motivation for sort of looking at the stuff at the stuff in the first place, because somehow, sort of, in the world which I understand, I mean, I sort of understand how this works, and somehow quiver varieties have always been very mysterious to me. And so somehow, so the idea is that the quiver varieties here, from this point of view, they kind of appear as symplectic duals to what comes from sort of geometric static correspondence. Okay, so this is again, so I mean, again, it's just an example of some geometric structure you expect. So in fact, I made a list of various geometric facts I can think of, and this list contains 12 items. I'm definitely not going to explain all of them, but just the idea is that, unfortunately, at this point, somehow there's no kind of sufficiently good systematic way to sort of, I don't know, formulate one conjecture which would imply everything. But this is just an example of things which should appear here. Okay, so what one would what we would like to do is, so what do we want? We want, first of all, understand how to construct duals in some reasonable generality, and so want some kind of uniform construction of this dual. So somehow some kind of, it's not just case by case construction, but some kind of uniform way to do it, at least in a certain generality, and so that will be applicable to proving at least some of the statements that I explained. And so for instance, I am going to explain some kind of construction which at least turns out to be sufficiently good for proving this kind of categorical symplectic duality. And that's kind of one thing we want to understand. And another thing we want to understand is what is sort of the right structure here. But where by the right structure, I mean that some kind of mathematical structure which should in particular contain in itself x and x check, but it should contain somehow more. So some kind of mathematical structure which sort of out of which we can construct this x and x check, but somehow the structure should be somehow much richer. And so mostly I'm going to talk about this next time. So let me give you some kind of glimpse into actually part 2. So actually the plan for the next time will be the following. So plan for tomorrow is first do one in case in the case let me say starting from a pair Gn where G is a reductive group and N is a representation, and in this case X will be T star of N reduction by G, and X check will be something, and so this is what I'm going to explain what X check is in this case. And then I'm going to try to say something about 2, so somehow the slogan is that the right structure is called three-dimensional n equal 4 supersymmetric quantum field theory. And I'm going to try to say what these words can mean mathematically. We'll try to say, so in other words, I'm going to try to define some kind of purely mathematical structure which is sort of supposed to capture enough of this in order to do everything we want. And I'm going to try to explain how to construct this much richer structure in this case. And explain how it allows to construct X and X check. Well, that's kind of definitely an ambitious plan for tomorrow, but that's what I'll try to do tomorrow.